Chemical reactions. In this lesson, we'll be covering chemical reactions, reactions and products, describing chemical reactions, symbols and equations, energy and chemical reactions, and then we're going to do some practice. Describing chemical reactions. Objectives. Number 1, describe how to write a word equation. Number 2, describe how to write a chemical equation. Chemical reactions. Chemical reactions express how atoms combine or split apart to form new substances. So for example, H2 plus O2 gives us H2O, so that's our atoms combining to form a new substance, H2O. CH4, methane, plus oxygen gas is going to give us carbon dioxide and water. In the second equation, we're seeing an example of both combining and splitting to form two new substances, carbon dioxide and water. All chemical reactions have two parts. Number 1, the reactants. The reactants are the substances you start with, and then we have the products. The products are the substances you end with. The reactants turn into the products. So usually we write it as reactants yield our products. So if it were math, the reactants would be the question. So for instance, 2 plus 2. The products would therefore be the answer, 4. The reactants turn into the products. So our reactants, 2 plus 2, and our product, 4. Describing chemical reactions. A reaction can be described several ways. Number 1, a word equation is a way of describing a chemical reaction using the names of the reactants and the products. So for example, iron plus sulfur is going to give us iron 2 sulfide plus energy. Now keeping in mind, this lesson isn't about predicting, so you're not to know that iron plus sulfur is going to give us iron 2 sulfide. You just need to understand what this word equation means. So iron plus sulfur yields iron 2 sulfide plus energy. And number 2, a chemical equation is a way of describing a chemical reaction using chemical formula of the reactants and products. So for example, the same example above would be written as Fe plus S gives us FeS plus energy. Again, we're not here to predict, we're just here to understand and explain what these mean. Symbols and equations. The arrow separates the reactants from the products, so the arrow is going to point to the products. So for example, in the first one here, we're going to have zinc plus copper sulfate yields or produces zinc sulfate plus copper. So we're going to read this as reacts to form or yields. The plus sign equals and, meaning that they are reacting with each other. So on the left-hand side, we have zinc and copper sulfate, or zinc plus copper sulfate yields zinc sulfate and copper. Symbols continue. So we're only going to use our symbols in our chemical equations. The symbols include a description of the state of the reactants and the products. So for example, S is solid. So if you have FeS, that's solid iron. You'll notice where the S is. So it's going to be a subscript to the right. So we're always going to have our symbol, and then our subscript is going to be down to the right in the spot right here. If you just have a generic atom like X, then our subscript would be down here. Now that subscript is going to be for the number of atoms, but also the state. So really you could have two subscripts. So this could be written as X2 solid. And we see that with our second example here with our gas. So the G after the formula equals gas, so CO2 gas. L after a formula is going to be for liquid, so for instance H2O liquid. AQ after the formula means it's dissolved in water. We call this aqueous solution. So NaCl is NaCl and then AQ in brackets in the subscript. And this is a saltwater solution. If it's aqueous, it means it's dissolved in water, so it's always going to be a solution in water. So a good example of showing these different symbols is our previous example. So we have zinc solid, you can see solid because it's the S beside it, plus copper sulfate, aqueous, so that means that's dissolved in water, yields zinc sulfate, aqueous, plus copper solid. So what this means is this equation is actually going to produce a precipitate. In this case, it's going to be a solid copper precipitate that's going to come out in the solution. So if you were to mix solid zinc with aqueous copper sulfate, you're going to end up getting a solid copper as a result. Energy. A net or resulting amount of energy can either be absorbed, used, or released, created. If the net energy is absorbed, it's written on the reactant left side. So you can see in this example here, a net energy is used. If the net energy is released, it's written on the product side, as you can see in the second example. This doesn't mean that there's no energy used in the reactant on our second example. The difference is there's more energy produced. So you could write it as this. So for example, if I want to visualize what this looks like, it might be energy, little energy, and then on the product side, it might be a lot of energy. So since there's more energy on the product side, we only write it on this side right here, because it just kind of cancels out. Another way of looking at it could be if we say had 2 energy, just for simplicity's sake, and we produced 4 energy. Since there's more energy on the product side, it would just be like saying, okay, well, we had a net of 2 energy on the right and 0 energy on the left. And that's why we write energy on the right-hand side, because there's more energy produced than used. In the first example, it's the opposite. There's more energy going to be used than produced. So we don't write it on both sides and say, okay, well, there's more energy on the reactant side. We simply write it on the reactant side saying there's a net amount of energy used in the first equation. There's a net amount of energy produced in the second equation. Energy. So take a look at a couple of examples of this happening. So if the energy net is absorbed, energy is written on the reactant side like we had in our previous example. That means it's taken away from the environment. That makes it feel cold. And that's what these instant cold packs do. There's a chemical reaction for the two substances inside the cold pack. When they react to each other, they're going to suck a lot of the heat out of the air. When they suck a lot of heat out of the air and in the environment of the actual cold pack itself, the cold pack feels cold. An example of the opposite kind of reaction is when the net energy is released. So energy is written on the product side, and this is because it's sent into the environment, and it's going to feel warm. Heat is released. An example of that is fire. So there is some energy used in the creation of the fire, when you're striking the match, when you're rubbing the sticks together, but there's a lot more energy on the product side. There's a lot more resulting net energy than there was in the creation of the fire in the first place. So what I want you to do is I want you to pause the video and I want you to write in a chemical equation for these two examples here. So remember, chemical equation is when you can use the symbols to represent what's going on. Okay, so let's work them out. So solid iron 3 sulfide. So let's figure out what iron 3 sulfide is. Iron is Fe, we know it's 3. Sulfide is 2 minus, and when we cross them, we're going to get FeS. The 3 is going to go down here by the S, the 2 is going to go down here by the iron, and we know it's solid because it says it right there. So we're going to write solid. Reacts with, so that's plus, gaseous hydrogen monochloride. So we're going to say hydrogen monochloride. It just says monochloride and nothing in front of hydrogen because we don't write mono in front of the first. So it's just HCl, and it's gaseous, we're told that. So we're going to write gas. To form, so we know that that's the arrow. Iron 3 chloride gas, let's write that out again. Fe, remember that's 3 plus. Chloride, that's Cl negative. We're going to cross them, and we get FeCl3, and we're told that it's a gas. So comma, so that's going to be and. Dihydrogen monosulfide, so dihydrogen monosulfide, gas, plus energy. Number 2, using energy, so we're going to say energy. So using energy, aqueous sodium chloride, so we're going to plus sodium chloride, aqueous, remember sodium is Na plus 1, chloride is Cl negative. So aqueous sodium chloride, after we switch them, we get 1 and 1, forms, so arrow, aqueous sodium chloride ions. So sodium ion looks like that, chloride ion looks like that. It's forming both of them, and it says aqueous. So you write AQ, and we're done. Pause the video and write the word equation for this example here, keeping in mind that states are not included in our word equations. Okay, so word equation, we're going to start off by writing energy. Now keep in mind, this is not a sentence. This is an example of a sentence right here, where it's using full words, full sentences. A word equation is where we just have the words. So energy plus, okay, Fe, so we say iron, plus O2 is oxygen gas. Don't forget the gas. Arrow. Now this guy here, we're going to have to figure out what it is. So we're going to have to do the reverse crisscross. 3 plus, 2 minus. We check. Oxygen is indeed negative 2. So we know that that iron is going to be 3 plus. So we're going to write iron. 1, 2, 3. Oxide. Catalyst. A catalyst is a substance that speeds up a reaction without being changed or used up by the reaction itself. Enzymes are biological or protein catalysts in your body. And keeping in mind that without enzymes, our bodies couldn't do the chemical reactions required to keep us alive. So this is a term you need to know. So catalysts in general are a substance that speeds up a reaction without being used up. And enzymes are specific catalysts that are used in living things to ensure that the chemical reactions happening inside goes at a fast enough rate to keep that organism alive. And that concludes our lesson on chemical reactions.